In this video, we will continue our exploration of Norton's theorem. In Thevenin's theorem, we said that a linear two-terminal circuit can be replaced by a Thevenin's equivalent circuit, which is a voltage in series with a resistance. This equivalent circuit is said to have the same effect on the load as its original circuit. In similar manner, the same linear two-terminal circuit can be converted into a Norton's equivalent circuit, which consists of a current source in parallel with a resistance. This equivalent circuit will also have the same effect to the load as its original circuit. Since we're talking about the same linear two-terminal circuit, we can conclude that these two equivalent circuits, the Thevenin's equivalent circuit, is equivalent or equal to the Norton's equivalent circuit as far as the load is concerned. So let's give focus to these two equivalent circuits. Say that we want to convert these Norton's equivalent into a Thevenin's equivalent circuit. Let's see what happens. So I remove this part of the circuit. So I get an open circuit and then I measure the voltage across that open circuit. So that is a voltage VOC. And since this is an open circuit, this current will simply flow towards the resistance R sub n. Therefore, a voltage will be developed across that resistance where the plus is here and the minus is there. Since this voltage or R sub n is also across the voltage VOC, I can conclude that VOC, which is my VTH, also would be equals to the voltage across R sub n, which is I sub n times Rn. Also, if I want to get RTH, I can disable this independent current source, giving me RTH equals R sub n. Now that I have found VTH and RTH, I can replace this circuit with this one. So it's a voltage source equals to INRN. So this one comes from that. And this is our RTH, which comes from that. Okay. Now, since these two circuits are the same, we can conclude that this part here must be this part here. So that means that VTH, the VTH here must be equals to this one, INRN, and RTH equals to R sub n, which is actually also this one. And therefore, I can say that solving R sub n, I can get it from this equation, and that will give me the ratio VTH divided by I sub n, which is also equals to RTH. So therefore, there is a third way of getting R sub n or RTH, and that is getting the Thevenin's voltage, VTH, and the Norton's current, I sub n. Let us have an example to illustrate case 3. Here in this problem, we are required to solve for the voltage V sub x, which is the voltage across the 1 ohm resistance. Take note that we have here a dependent current source, which is dependent on the current I sub x that is flowing through the 1 ohm resistance. Also, as stated in the example, we are required to use the shaded portion of the circuit as the circuit that will be converted either into a Thevenin's equivalent or a Norton's equivalent. So let's get the Thevenin's equivalent first of the shaded portion. So after getting the Thevenin's equivalent, that should give us a more simpler circuit that would look like this one. To find VTH, we remove that part of the circuit that won't be converted, so that will leave us an open terminals. So these are my open terminals. So let's say we call this terminal A, and this is terminal B. So we want to know this voltage across the open terminals. So this is POC here, and this should be plus here, and this is minus. Now take note that this current depends on the current that flows here, which is designated as I sub x. But since this is now an open circuit, I sub x there must be a 0. So this must be a 0. And this current source here, since it is 5I sub x, must also be a 0. Okay? And a 0 current means that this current source must be non-existent. It's like being disconnected from the circuit. So this would give us a much simpler circuit that looks like this one. And now, because that there is no more source here, that means that the 2 ampere current will simply flow directly to the 2 ohms and then to the 4 ohms and back. Uh, that means also that the voltage across the 2 ohms, uh, the polarity would be plus here, here would be minus, and for the 4 ohms, this will be the plus, and this will be the minus. To solve VOC, I look for a loop that does not contain a current source and traverses VOC, and this should be this loop here. Okay, so from there I can write my KVL equation as that one. So minus VOC plus 2 times, I combine the 2 and the 4, so times 2 plus 4 equals 0. And from there, I can get my VOC. Now let's compute for I sub n. Again, we remove the circuit that is not part of the conversion, and that will result in an open terminals, and we apply a short across those open terminals and determine the current flowing from A to B. Here, the current I sub x is not anymore 0 because it is not an open circuit, and therefore 5ix must not be a 0. We can apply KCL on this node to determine this current, and that should give us 6I sub x Okay, so 5 plus 1 here plus 2 amperes. Okay, so that current flows towards this node, and again applying also KCL on this node to get this current. The current here must be 6ix plus 2 minus 5x, so that would give us I sub x plus 2 here. Okay, the polarity due to the currents must be positive here, negative, positive, negative. We can determine I sub x by writing a KVL equation around this loop. So this loop does not contain a current source, and that should give us this equation. So starting at the 2 ohms, that would be plus 2 times the current, which is 6ix plus 2, plus 4 times the quantity I sub x plus 2 equals 0. And from this equation, we can extract I sub x, and that should give us this answer. Now, to get ISC, or the short circuit current, notice that the direction of ISC is opposite of I sub x. So therefore, ISC must be the negative of I sub x, and that should give us this answer, which also is our I sub n. Now that we have both VTH and I sub n, we can determine RTH using case 3 by getting the ratio, and that should give us 16 ohms. We can then draw the modified circuit, where this is our RTH and this is our VTH here. And applying KVL around this circuit, so this is just a single loop, so minus 10 plus 1 plus 16, 17 Ix, then plus 12 equals 0. And that should give us an Ix, which is this one. And from there, we can compute for V sub x, which is simply 1 Ix.